Recording.
Today we are going to discuss the intermolecular forces of attractions. If I remind you, so it's the same thing. It's actually the continuation of the same thing, which we have been previously doing. A covalent bond. And whenever there's a covalent bond, we know that there are two types of structure. One is simple molecular structure, and the other one is, yes, macromolecular structure. So currently, or giant molecular, you can also call it. So then we are just doing this thing still. Simple molecular structure when there's a covalent bond between the atoms and a very small number of atoms, 2, 3, 4, they join to make a tiny molecules, right? That is known as simple molecular structure. We gave you the example H2O, CO2, etc. Right? That was their dot. Then we had their dot and cross diagram to explain the bonding in them. And then we said, what are the shapes of the molecules? And then we see how the polarities are. And now in continuation that, today we are going to see if we have a one water molecule, another water molecule in a beaker, what is the force of attraction, or if there any force of attraction present between the molecules of water? Yes. So this is what today we are going to see. This is intermolecular force, IMF. So I hope you got my point. This is not within the molecule. This is one molecule to another molecule. So this is what today we are going to discuss. Okay, how the molecules which are formed, covalent bond and simple molecular structure, how these molecules are held together if they have any force of attraction. We say yes, they do have forces of attraction present between them, and those forces of attraction are known as intermolecular forces of attraction. I hope it's clear now. So intermolecular forces, the forces of attractions between the molecules. The forces of attractions between the molecules. All right. Now, as far as this is concerned, there are two main types. Please write down. There are two main types. There are two main types. Number one, van der Waals forces of attractions, and number two, hydrogen bond. Yes, hydrogen bonds. The first one is, number one is van der Waals. Okay, now let me explain them first of all, and then I'll explain them all together, and then I'll make you write one by one. Okay? So now, for the sake of explanation, I need your attention, undivided. So, what are these van der Waals forces? Let's see. Let me give you three examples here. Look, this is a beaker containing HCl. These are the molecules of HCl. Okay? In the last class, we studied that when the bond is formed between two atoms, it's a diatomic. Chlorine has more electronegativity. So this side is going to get what? Partial negative. This side is partial. So HCl molecule is polar. Yes. So then we have clear understanding in this point. Okay, that's pretty much straightforward. When the positive end of one molecule naturally going to attract the negative end of other molecule, because the dipole's one end, the positive end, is going to attract the dipole's other end. This is the intermolecular force that is going to be formed between these two molecules. Is it? Yes. And this force is known as dipole, dipole, yes, force of attraction, right? So it is pretty much straightforward. In all those polar molecules, the positive end of one dipole always attracts the negative end of other dipole. So between two molecules, this force of attraction is there. So this force is known as dipole force of attraction. Okay. On the other hand, if I write hydrogen here, now you know that hydrogen molecule is not polar. There is no charge separation. There is no partial negative. There is no partial positive. So then how this one molecule of hydrogen is going to attract the other molecule? Will it? And if it is going to attract, what type of force of attraction? Yes, we say although it is a non-polar at this moment, but when these two molecules of H2, these two, when they get close, then just like HCl, their electrons repel each other. It's just like this. Hydrogen is like this. The electrons is outside and nucleus is inside. So when these come close to each other, here, both electrons, the H2, one H2's electron and the other H2 molecule's electron, they repel each other. And as a result, again, just like this situation creates, just like this, that this side gets slight negative, slight positive, negative, positive. And here the force of attraction is developed here. That is again, is a dipole-dipole force. But now what is the difference? When dipole of one and the other dipole end attracting, it's the same force, obviously the same force. But the only difference is that these dipoles are not permanent. Yes, they are just induced. Why temporary? As soon as these hydrogen molecules get away, again, look, their dipoles are gone. Their dipoles are gone. They again become non-polar. That's why this force is the same, but we just change the name. This is known as dipole induced dipole force of attraction. You can call it DID. You can call it DD. This one was DD dipole force, and this is what? DI D4. So what I'm trying to say, forces are the same. So please mind this difference. These are not too different. If you just see what is happening in this case, the partial positive end of one molecule is attracting the partial negative end of other molecule. What is happening in this case? The partial negative end of one molecule is attracting the partial positive end of other molecule. There is no difference. The only difference is that these dipoles, these ones, are permanent. They were already there. But these dipoles, they are not permanent. They are just induced. Induced means created. They're just induced when these two molecules are close enough. And as soon as they get away, the dipoles are gone. So that's why you call it, these are the temporary dipoles, induced dipoles, right? So the force is the same. Therefore, both of them are known as VDWs, van der Waals forces, because technically there is no difference between them. The only difference, if the molecule has no permanent dipoles, they get close, they develop the permanent dipoles, negative end of one dipole attracts the positive end of another dipole, the force is known as temporary dipole induced dipole. Okay, you can call it ID forces. And you can call it PD forces, permanent dipole, right? So I hope you got that. All those covalent molecules, which are polar or non-polar, they do have van der Waals forces. But if they have already poles, the permanent poles, then the force of attraction, the same force of attraction, the negative end of one dipole, the attracts the positive end of the dipole, is known as PD or DD. If there are no permanent dipoles, again they are created. So whenever these two hydrogens are close to each other, then at that moment there is no difference between the molecule of HCl and molecule of H2, because they are also polar now. Okay, and now the positive end of one dipole attracts the negative end of the dipole. This force is known as dipole induced dipole, temporary dipole induced dipole force, right? So this is how you look at the VDW. So all those molecules. Now, if the examiner asks you, now what they are going to ask you, now I hope you got it, what I'm trying to say. What they ask you, the examiners are doing this thing, that they ask you, for example, carbon monoxide, CO. And there is other molecule, nitrogen gas. These are the two gases. So what they ask you? Okay, what are the intermolecular forces present in the molecules of nitrogen gas and in the molecules of carbon dioxide, carbon monoxide gas? Carbon monoxide, I know, is a polar. Already permanent dipoles are there. So what is the force of attraction? PD. Okay, in the carbon monoxide, there is a one molecule of carbon monoxide. There is another molecule of carbon dioxide, carbon monoxide. Here is the force of attraction. When the positive end of one molecule attracts the negative end of the molecule, and the force is known as PD, permanent dipole, because they are already there. But in nitrogen gas, there are no permanent dipoles. So in this case, they have to generate the dipoles just like this, right? And here the force of attraction that is developed, when they develop the dipoles like this, for example, the force is the same, but this is known as ID. What is the meaning of this? Induced dipole forces. Okay, they are known as ID. Why? Because there were no permanent dipoles. They were just developed when they come close to each other. Rest, the detail is the same. When they develop the dipole, when the negative end of one dipole attracts the positive end of other dipole, rest detail is always the same, right? So this is how we look at these forces. Do you have any question?
Yes. What would be the full exact definition of a dipole if they ask in the
Yeah, the charge separation that takes place due to the difference of electronegativity is known as bond polarity or polarity. Yeah, the same definition. Okay. Okay, next is look at this. So here is carbon monoxide, PD forces, nitrogen is what? ID forces. Now, moving on. If you look at hydrogen fluoride here, look at this, kids. Okay, now hold on, just for a minute. Now, what did you say? Here is the ID forces. But one thing which I want you to understand, Minahil, can I have your attention, please? No, I need your complete attention. Oh, sorry, I thought you're using phone. No, but I need your complete attention. Okay. Look at this. Is this a polar molecule? Permanent dipoles are there. At times, what happens in the polar molecules, look at this. They come like this. If two carbon monoxide molecules are close to each other like this, are they going to attract or repel? So in this particular case, again, when they repel, the temporary dipoles are induced here, right? So when the temporary dipoles induced here, the force of friction that is going to be developed is what? ID forces. So I hope what I'm trying to say, and you are getting it, that the polar molecules have both type of forces. Permanent and induced. Because their permanent dipoles are not always attracting each other in the opposite way. If they come negative in front of the negative, because of the repulsion, there are some instances where the temporary dipoles are induced in them. And when the temporary dipoles, now let me explain it again. Okay, now let me explain it again. What I'm trying to say, that if this is the carbon monoxide molecule having the permanent dipoles, and there is another carbon monoxide molecules, right? And here is the force of attraction between them. Okay. Now this force is what? Now this force of attraction or repulsion? So when they repel, they have to induce to the temporary dipoles. The electrons of this are going to go to this side, let's say. Okay. So because of this repulsion, here are temporary dipoles induced. And because of temporary dipoles induced, the force of attraction developed is known as dipole induced dipole. Now you got it? What I'm trying to say is the ones which have permanent dipoles, they have both type of forces. Dipole and dipole induced dipole. But those who are non-polars or having no permanent dipoles, they have only dipole induced dipole forces, right? So please write down carbon monoxide has both VDWs. Both VDWs mean DD and DID forces. But nitrogen has only DID forces. Okay? As this is polar and this is non-polar. So a non-polar molecule has only one VDW and polar has two VDWs. Okay? Now, what the examiner asks you at time, for example, what are intermolecular forces present in A, carbon monoxide, B, HCl, C, carbon dioxide, D, ICL. Can you please just write the names of intermolecular forces? Anyone?
It's
Okay, now carbon monoxide has a permanent dipoles. So its intermolecular forces are both DD and DIDs, or PDPD or IDID. HCl is what? It's a polar, so contains both. Carbon dioxide, it's a non-polar. The other day we found out the overall bond polarities cancelled out each other. The dipole moment for the carbon dioxide was found to be zero. So it's a non-polar. So when it's a non-polar, only DIDs or IDID forces. And the last one, ICL, it's a polar, so it has both. Yes. So again, they ask you the same question. Now they ask you what are the intermolecular forces present. Now the same question they may ask you like this. What is significant or strongest intermolecular force in the followings? Okay, what is the strongest intermolecular force? Significant or strongest? Which one? The first one. When they are both present, obviously, DD forces are strongest or significant. Again, DD, carbon dioxide, as they are only DID, so the DID forces are there. And ICL again, DD. So I hope you understand now what they ask you the question, you have to carefully answer it. Okay? Yes, if the hydrogen bond would have been there, that was the significant or strongest intermolecular force. But in this case, right? Yeah, I'll come to that in a while. Just give me a few more moments. Excuse me. Now, is it clear? Now, one more thing. The strength of kids' DID forces depends on, look at this, the strength of DID forces depends on number of two factors. Number one, number of electrons primarily in a molecule. And number two, number of electrons in a molecule. And number two, shapes of molecule. Now let me explain it. This is straightforward. For example, I have fluorine molecules and I have iodine molecules. Okay. Fluorine is non-polar. Obviously, it's a non-polar. So what type of force is going to be? DID. Dipole-induced dipole forces. IDID. But there are 9 electrons in one atom of fluorine. So total how many? 18 electrons. Here is the molecule of fluorine, let's say. The other one has the same. Similarly, if I ask you, what about the iodine? They are again non-polar. What type of forces? DIDs. But you know, one iodine has 54, another has 54. How many electrons in total? 108. So obviously, I think very commonsensically, we can say clearly, here are the more electrons, here is the more repulsion, here are the stronger dipoles created. Am I right? So obviously, here is the force of attraction that is going to be stronger. The forces are DID in both these cases, in F2 molecules and I2 molecules. But the I2 molecule forces are way, way stronger. I can give you an evidence in this particular case that fluorine exists in what state? Gas state, which tells us there are no or very weak intermolecular forces. Iodine exists in what state? Solid state, which tells you that there are strong enough forces of attraction between the molecules, because solids have a strong intermolecular forces, strong forces, right? So this is the evidence. So whenever there are more number of electrons in a molecule, there are stronger dipoles, the temporary dipoles induced, hence stronger DIDs. Okay? So this is a major factor which affects the strength of DIDs or van der Waals forces. They are going to ask you again and again. I'll explain in the next part, but I hope you got it now. Next, the shape of molecule. Shape of molecule is not pretty much important here. It goes with the organic, but I'll just give you an information on need to know basis. For example, look at this. If I have CH3, CH3, look, and I have same size of the molecule like this. If you remember, this is the same C4H10, but one molecule is branched and one molecule is unbranched. Now, two unbranched molecules, they have intermolecular forces like this. Do they have more surface area in contact? So obviously here, the more force they are going to generate, because they are both non-polar. It's just like I put two pens together like this and put a glue. So they have more surface area. They are very strongly attached. If I put them in this way, the same pens, they have less surface area in contact. So they have less forces. Similarly, look at this. If you see this, what do you think? Where is the more surface area? Over here or over here? That one? So it means molecular size same, but the strength of intermolecular forces would be higher. Strength of DID forces would be greater in this unbranched. Okay, hence it's going to have a higher melting boiling point. Okay, so this is how the shape also matters, but primarily the number of electrons. Okay, so now I'm going to sum up before going to the hydrogen bonds, that the forces of attractions, when the compounds form, let's start, when the compounds form covalent bonds, they form tiny molecules. Those tiny molecules attract each other. Their forces are known as intermolecular forces. If that tiny molecule is polar, the force is dipole-dipole. If that tiny molecule is non-polar, the force is dipole-induced dipole. But the polar does have dipole-induced dipole forces as well, because their temporary dipoles are also induced. Okay? And the last thing, that the strength of DID depends on the number of electrons present in that molecule. The more number of electrons, the stronger DIDs. Okay? So that creates the more force of attraction between the molecules, right? And the shape of the molecule also matters. For example, in case of an organic compound or molecule, the branched has less intermolecular forces as compared to the unbranched, because they have more contact area, they have more dipole-induced dipole forces, right? Now, moving on to the third type, the second main type is the hydrogen bond. Now, if you look at, before I go to the hydrogen bond, formally, if I ask you about this, anyone, ये polar है, what about this? क्या होगी force of attraction here? What is the force of attraction? Sorry? There are the permanent dipoles. What should be the force here? Excuse me. Isn't it the permanent negative end of one permanent dipole attracting the positive end of other dipole? It shouldn't be PD. Yes, it should be, but it is not. This force of attraction is hydrogen bond. A while ago, the same force, what I was giving name, here it is known as what? PD or dipole. Why? What is the difference? There is a hydrogen.
Hydrogen bonded to FO, and fluorine, oxygen, or nitrogen is always a hydrogen bond. When it's not bonded to those, is a variable force.
So yes, precisely. When the hydrogen is covalently bonding with three elements, which three elements? Nitrogen, oxygen, and fluorine, FO and FON. So then hydrogens, these partial positive and partial negative charges, become significantly high. So then they are going to attract each other with a much stronger force than DD or PD. This force is known as hydrogen bond, right? And one additional thing which we are going to use, it's about the lone pair of electrons. So actually the lone pair of electrons of fluorine also involved, and they come and make a hydrogen bond, force of attraction with the hydrogen, right? So first let me tell you, there are, please write down with the star, there are actually three conditions in which I just wanted to let you know that it's not a different force, again, the hydrogen bond. It's the same PD, but under some circumstances, where a very strong force becomes hydrogen bond. So there are three conditions in which the permanent dipole force becomes hydrogen bond. Number one, the negative end of dipole, negative end of one dipole must be nitrogen, oxygen, or fluorine. The positive end of other dipole must be hydrogen. And third thing, this hydrogen should be covalently bonded with nitrogen, oxygen, or fluorine. These are the three conditions. If these three conditions are not there, it's a PD. If these three conditions are there, it is dipole, it is hydrogen bond. Okay? So in definition, you can write it when lone pair electron of highly electronegative atom of one dipole attract partial positive charge hydrogen of other dipole. It is known as hydrogen bond. Now, following these conditions, looking at the conditions, looking at the definition, it seems a bit harder, but let me make it simplified. OH, NH, FH. If one of these covalent bonds present in the molecule, that compound will have the intermolecular force hydrogen bond, right? So this is the simplest way of identifying it. If a compound has one of these bonds, so it means its intermolecular force is going to be hydrogen bond, right? So you just look at these bonds. Okay, for example, number one, water. If I look at the formula H2O, if I look at the dot and cross, does it contain one of the above mentioned bonds? OH, NH, FH? Yes. So I know that one water molecule is attracted by other water molecule by means of hydrogen bond as a DID to सब में ही होती है ना DID is still there. So this is the hydrogen bond. Now, as far as the drawing is concerned, as I told you, you have to draw the lone pair of electrons, and then lone pair electrons of highly electronegative atom attract the partial positive charge of other, and you have to show all the charges, please. Like this. And this water molecule has ability to make hydrogen bond all the way around because oxygen has two lone pairs, so both lone pairs can be used. This one. When the examiner asks you, you have to show just one side, but I'm showing all the sides just to make you understand that one water molecule can make hydrogen bonds like this. All sides. Okay, but once the examiner asks you, you just have to draw this part only. Okay? Number two is ammonia. NH3. If I draw the dot and cross and see, look at this. N, H, H, H. Does it contain any one of the following bonds? So its intermolecular force is going to be hydrogen bond. And how you have to show? Use this hydrogen with the next nitrogen. You have to draw all the charges like this. This is hydrogen bond. Urea. I would like you to show the hydrogen bond in urea. Does the urea molecule contain hydrogen bond? Yes or no? NHOH is there. So if I draw another molecule of urea here, so can you show the hydrogen bond, please? Please draw the urea. Are you done, urea? Look at this. This side is partial positive. This side is partial negative. I hope you have shown this. Okay. But urea also have, what is this force? Can you please elaborate? Yes, urea also have DD. And DID is always there. So urea is the molecule that contains all three type of intermolecular forces. Which one? Hydrogen bonds, DD and DIDs are always there in any molecule, right? What about the methanol? Now listen everyone. Although methanol has two hydrogens, this hydrogen is also partial negative, this hydrogen is also partial negative, but there is a difference. I cannot use this hydrogen. For example, do you think this will it be the hydrogen bonds? Why not? Is this a hydrogen bond? Why not? The hydrogen of one. Yes, this hydrogen should be covalently bonded with. Yes, and it is bonded with what? So this force is PD. Okay. On the other hand, if I use this hydrogen, then what about this? Why the hydrogen bond? So please mind this difference. In methanol, there are two types of hydrogen, but only the hydrogen that is attached with oxygen, that can make hydrogen bond with the next molecule. The other hydrogens, they can make DD or PD, but not the hydrogen bonds. Okay. Now one more example. What about this? Methanol. HCHO. HCHO, बच्चों. Here. Why not? Yes, although there are the polarities, but no hydrogen bond. Why no hydrogen bond? Because there is no OH, NH, FH. Its intermolecular forces will be dipole, OP. But on the other hand, if I mix it with water, or if I mix it with ethanol, do you think it can have the hydrogen bond? What do you think? I believe so. Yes. Yes. Yes, it can. Yes, it can. Can we use these hydrogens for the hydrogen bonding thing? No. But we can use this oxygen for the hydrogen bond. If this oxygen is attracting with hydrogen of water, because that is the one which is attached with the oxygen, okay? Then this force is what? Okay? But not the ones which is down, okay? So when you mix methanol with water, it makes a hydrogen bond. That's why methanol is soluble in water, right? We'll see how the properties are affected by these intermolecular forces in the next class, right? And we'll follow a couple of more examples of hydrogen bonds in the next class, right? And we'll wind up this chapter in the next class with all the questions related. That's all from my side. Thank you.